All right, let's get started. So I just want to start off. We're not going to get here quite yet, but I want to start off by saying these are things that you need to get comfortable with. They're things you saw in 17B, and they're coming back now. So make sure that you are very comfortable with, for a 2x2 matrix, that the determinant of a 2x2 matrix is the product of the diagonals minus the product of the off diagonals. So A times D, A and D are the diagonal elements. B and C are the off diagonal elements, and the product of A times D minus the product of B times C, that is the determinant of your matrix A, or whatever you decide to name your matrix. The other things you want to be super comfortable with are easily calculating the inverse of a 2x2 matrix. It is super straightforward once you know the pattern. The inverse of a 2x2 matrix A, if it exists, and it only exists if the determinant of A is non-zero, right? Because if that was zero, we couldn't divide by zero. But A inverse is equal to 1 divided by the determinant of A, whatever number that happens to be, as long as it's not zero, multiplied by, you take your matrix A and you switch the diagonal elements. So A and D interchange places. And the off diagonal elements, you change their signs. So if they were positive, now they're negative. If they were negative, now they're positive. That's always how we're going to calculate the inverse of a 2x2 matrix. It's very easy pattern to remember after you've done it a few times. Thirdly, and this one we'll see all these in examples. I just want you to be aware that if you are not comfortable with any one of these things, you need to find the time to practice it, because you're going to be doing this over and over and over and over again. Thirdly, the way we're going to find eigenvalues of A is by solving this equation. The determinant of A minus lambda times the identity matrix, which is the 2x2 matrix with a 1, 0, 0, 1, equal to 0. We're going to do all of that today, but just so you know, you should practice this. You should look in the book, find some matrices, and just find the determinant, find the inverse, find the eigenvalues. Do that like 5 times or 10 times. Good practice. You're going to be doing it a lot. Okay. So kind of let's talk about what we're doing here. One other reminder, and he did kind of talk about this in class a little bit. So just as a reminder from 17B, and I'll try to use his notation as well, even though it's not one I particularly love. So I would prefer to write dx dt equal to alpha times x, or x of t. But he really likes the dot notation. So the dot notation for derivatives is specifically for derivatives with respect to time. So when someone writes x dot equal to alpha times x, it means the same thing. It just means that the derivative of x with respect to time is equal to a times x. If someone wrote dy dx, they wouldn't write y dot. They would write y prime. I might still use other notation, like I would probably write dx dt, because that's just what I'm used to writing, but this is perfectly fine. What I want to point out about this is we know the solution to this system of equations. This is a differential equation, has a derivative and the function, right? We're thinking of x as a function of time. That's why we're able to differentiate it with respect to time. Otherwise, that wouldn't really make sense. So when solving this, we can talk about what the solution is, but I'll point out we know how to solve this separable differential equation. You can rewrite, and I'm going to rewrite it the way I like to write it. You can write dx dt equal to alpha times x of t. I'm going to bring all the x's to the left, all the t's to the right. So I'm going to have 1 over x times dx equal to alpha times dt. And then after we separated the variables, that's when we get to anti-differentiate both sides. So the integral of 1 over x dx is equal to the integral of alpha times dt. And if we integrate both sides, we are going to ignore the absolute value here because it kind of more, well, actually, I'm not going to ignore it just so you can see why we get to ignore it. So we're going to, I don't need to write that symbol anymore. We're going to get the natural log of the absolute value of x equal to alpha times t plus a constant c. Now we're going to solve for x. So e both sides. So e to the natural log of the absolute value of x equals e to the alpha t plus c. E to the natural log of some stuff is just the stuff. E to the alpha t plus c is e to the alpha t times e to the c. That's the additive law of exponents there. And then we typically like to rewrite e to the alpha t times e to the c. We're going to think of e to the c. Well, c is a constant. e to the c is also a constant. I think he called it x naught in class. That's what I seem to recall him writing it as. You can really call it anything you want. So we're gonna rewrite this as well. I'm gonna be smart. I always forget to do. I'm gonna be smart. So before I write that, I'm gonna say that dropping the absolute value. Sorry, if the absolute value of x is equal to 5, what could x be? Let me say that again. If the absolute value of x is equal to 5, x could be 5 or -5. So if the absolute value of x is equal to something that's for sure always positive, e to the something is positive, e to something is positive, that means that x as a function of t is equal to plus or minus, and watch how I write this. I'm going to put the e to the c first. So plus or minus e to the c times e to the alpha t. And now I'm going to say that plus or minus e to the c is just some constant. It's our initial value. I'm going to call it x naught. So that x of t is equal to x naught times e to the alpha t. And then I'll point out, we could have just not written the absolute value the whole time, right? If I had said just natural log of x, and then to e to the natural log of x, which is x was equal to e to the alpha t times e to the c, I could have just called that x naught and kind of ignored the fact that it was plus or minus, and you still capture that in there. So I would encourage you all, when you're doing these kind of problems, don't worry about the absolute value if it even shows up. And really, it's not really going to show up, but like we didn't really need to worry about it. We could have dropped it from the get-go and still gotten to our solution. And I'll point out that this is a solution, or is the general solution to the differential equation. Dx dt equal to alpha times x of t. And it works, right? Alpha times x of t is alpha times that. And the derivative of that, dx dt, well, remember the derivative of e to the stuff. Why am I saying words? Let's just write it down. This is the point, right? Dx dt, if I actually take the derivative of this expression here, the x naught hangs out, and the derivative of e to the stuff is e to the stuff times the derivative of the stuff, and the derivative of alpha times t is alpha times 1. But look, that's exactly my x of t times alpha. So the derivative of x is equal to alpha times x, as it should be. The reason we're talking about this is because we're going to see another version of it in now kind of more variables. So that's what's going on with this, all the stuff you talked about in class on Wednesday and Monday, is when you're talking about like all these like solutions to things and the matrices and all that jazz, it all comes back to kind of this being true. The fact that if the derivative of something is equal to a multiple of that something, then your solution is e to the alpha t times some stuff. Kind of great. All right, let's look at some examples. And we'll start off by actually doing the hard part first, and then we'll get to the easier part second. So let's find the eigenvalues and eigenvectors of the matrix, A equal to -1, 2, -3, 4. Whenever I'm reading a matrix, I'm always reading rows first and then columns, like first the first row, then the second row, then the third row. Okay, so here's how we find eigenvalues. We're going to solve the determinant of A minus lambda times the identity matrix equal to 0. We can write this out in a bigger way. So I'll say this in a minute. So we're going to solve determinant of our matrix A, which is -1, 2, -3, 4, minus lambda times the identity matrix, which is 1, 0, 0, 1, equal to 0. Okay, you can skip this step, because what this really amounts to is just writing the determinant of your original matrix, and in the diagonal entries, you're going to subtract lambda. So instead of writing -1, 2, -3, 4 minus lambda times 1, 0, 0, 1, I should really just write -1 minus lambda, 2 minus 0, -3 minus 0, and 4 minus lambda. Or in other words, whenever you're finding eigenvalues, you always start by subtracting lambdas in the diagonal entries, top left corner, bottom right corner, and then taking the determinant of that, saying equal to 0. For 2x2 matrices, which is all we're going to deal with all we're going to deal with in this class, you're always going to get a quadratic equation. See what I mean? So let's see. So product of the diagonals, so it's going to be -1 minus lambda times 4 minus lambda minus the product of the off diagonals, 2 times -3. I will point out something that you'll see later. If this part over here, if this minus part here happens to be 0, like maybe that's a 0 or that's a 0, there is absolutely zero need to multiply this out. It's already factored for you if you've got a 0 there. So don't do more work than you have to. If you've got a 0 there, just leave this as is and then find your eigenvalues. Here we do have to multiply it out. So let's see. Okay. Yeah, -1 times 4, -4, plus lambda minus 4 lambda plus lambda squared plus 6 equals 0. Rewrite this in the usual way. Lambda squared first. -4 lambda plus lambda is -3 lambda. And -4 plus 6 is +2. Many times this will factor. Many times this will not factor. I will tell you, you're going to see some imaginary numbers. You're going to get eigenvalues that are complex, having a square root of a negative, and that's okay. That means something. It means we're going to have a spiral. Whereas when your eigenvalues are real, it means we're going to have what's typically called a node, where everything points inwards or outwards. But we'll get more to that later. Solving this does factor nicely as lambda minus 2 times lambda minus 1 equal to 0. So our eigenvalues are lambda equal to 2 and lambda equal to 1. And I will say doesn't really matter, but you should give them subscripts. So I would say lambda 1 equal to, this is going to be kind of annoying, but I'm going to do it anyway. Lambda 1 equal to 2 and lambda 2 equal to 1. It doesn't matter which one you call which. It is often the practice to call lambda 1 the one that is the biggest, but don't worry about it at all. Just call them, do whatever you like. Lambda 1 equals the first one, lambda 2 equals the second one. Doesn't matter what order you put them in. Now, to find the we'll talk about that later. To find the eigenvectors, there's 2 ways to do it. They're really the same. I'll show you both ways. So let's start off. So for each eigenvalue, you're going to find an eigenvector. So for lambda 1 equal to 2, we want to solve, or I should say, we want to find the eigenvector v1 such that a times, do I want to do it that way or that way? I'm going to do it the way I like to do it first. A times v1 equals lambda 1 times v1. This is what's special about eigenvectors and eigenvalues, is that the matrix multiplied by the eigenvector is equal to a multiple of the same eigenvector. So writing this out this way, not super helpful yet, but now I'm actually going to fill in the blanks. So A is the matrix, -1, 2, -3, 4. V1 is the eigenvector, which I believe he was using the notation that we're going to call this V11, V21. I usually call it XY or X1, X2, or whatever letters you like to use. And then that's going to equal lambda 1, which we're picking 2 for this one, equal to 2 times V11, V21. And this matrix equation really represents 2 equations. Let's write them out. So the first equation is -1 times V11 plus 2 times V21 equals 2 times V11. And I was watching him, just watching the video, but not actually listening to it because I was in the meeting. So I was watching him do this, but I didn't know what actually words he was saying. I saw him do this and then write down the second equation, but I don't know if he said anything about that. But what I will say is that you don't actually need both equations. One of them is usually sufficient. So from here, what we then typically do is we solve for either V21 or V11, either way. So I would probably add V11 over here to get 2V21 equal to 3V11. And then the easiest thing to do at this point is to say that your vector V1, which is equal to V11, V21, pick any non-zero numbers that solve this equation. I'm going to make the easy choice and pick watch for a second, everybody watch. I'm going to pick V11 equal to 2 and V21 equal to 3. Because 2 times 3 equals 3 times 2. And that always works, and it's super easy. There are other ways to go about this. If I wanted to, I could have solved for V21 and said V21 equals 3/2 times V11. And then pick any number for V11 that I like, except for 0. Because 0, 0 is never an eigenvector. 0, 1 can be, and 1, 0, as long as one of the components isn't 0, you're fine. But if both components are 0, no bueno. So V11, if I pick V1, I would pick V11 equal to 2, and then 3/2 times 2 is equal to 3. I should also mention, this is not the only correct choice for an eigenvector. Any multiple, any non-zero multiple of this eigenvector is also an eigenvector that would be a perfectly valid choice. So it would also be valid to say, pick -4, -6. Or +400, +600, or really literally any multiple. Because once something's an eigenvector, it's really telling you the class of eigenvectors. Every multiple of this is also an eigenvector. Let's actually see that it's an eigenvector. Actually, before I do that, so I want to point out that if you looked at the second equation, it would have told you the same information. So the second equation here, which we can just write here for a second, which is -3 times V11 plus 4 times V21 equal to 2 times V21. If we do the same sort of solving here, I'm going to get, let's see, 4 minus 2 is 2 times V21 equal to, add the 3 over there, 3V11. That is literally the same equation I had from before. So both equations, with some rare exceptions, will always give you the same information, the same relationship. Occasionally, one of the equations will tell you absolutely nothing, and the other equation will tell you what you need to know. But you only ever need one of the equations to tell you the relationship between the variables, which will tell you the eigenvector. Now, what makes this special again? Well, if you take your eigenvector, I'm going to say 2, 3, because I'll say the vector that has integer values that are as small as possible is usually the kind of the standard choice. Like we could have done 1 3/2, that would also be an eigenvector, or divide by 3 2/3, 1. But this is the choice what everyone's going to make if they get to make a choice, typically. And then I'll just mention here that if you take your matrix A times your eigenvector V1, you get -1 2, -3 4 times the vector 2 3. If we actually do the multiplication, -1 times 2, actually let's just write it out, James. -1 times 2 plus 2 times 3 is the first row with the first column. And then -3 times 2 plus 4 times 3 is the second row with the first column. And if we actually simplify this, we end up getting -2 plus 6, which is 4, and -6 plus 12, which is 6. And that is exactly as prescribed 2 times the original vector, or 2 times the eigenvector. So it really, really, really should always be the case that once you find the eigenvector, the matrix times the eigenvector has to equal the eigenvalue times the eigenvector. You have no other recourse. There's something I want to say there. No, it's not. Oh, you don't have to check this though, right? So once you find the eigenvector, you're good to go. If you feel like you might have made a mistake finding it, then yeah, checking this multiplication is a good idea. But if your work is right, the eigenvector is the eigenvector, and there's nothing you have to actually check. Also, as always, you should stop me if you have questions. Some of you at the end of class come up and you're like, James, I have this guy. I'm like, this would have been the perfect question to ask in front of everybody because everybody would have liked to have known this. So if you think your question is just for you, it's not. Ask it for the sake of everybody. Be a good student citizen and help out your fellow students by asking the question so everybody gets to hear the answer. Maggie, you just stretching? No question. All right, let's look at the other eigenvalue, lambda 2 equal to 1. And here I am going to show you the other way of solving for the eigenvector. So I'm always biased towards not always. I'm usually biased towards doing it the way I just did it when the numbers are nice. But if the eigenvalues are kind of gross, like if your eigenvalues aren't integers, if you've got some irrational things like 1 plus the square root of 5 or something imaginary, we'll get there in a second. Doing it this way is actually typically better. So instead of solving a times v2 equal to lambda times v2, I should say lambda 2 times v2. I like this because it has the geometry, right? This is telling you, oh, your matrix times your vector should equal a multiple of that vector. It really kind of displays the geometry of the situation. But sometimes it's easier to solve this as a minus lambda times I times your vector should equal the 0 vector. So I know I feel like the notation he's using in class is a little bit like he's drawing as like X's with like maybe 2 lines on them, and like it seems a little bit challenging. I personally would choose to write my vectors as letters with arrows over them. That is a pretty standard notation for vectors. I'm sure you'd be fine writing it that way. So here we're going to do this. We're going to say, okay, well, a minus lambda. So remember, we already did a minus lambda 2 times I, but I'm going to write it again. So that's going to be really a, which is our matrix, -1, 2, -3, 4. And then we're subtracting our lambda, which is 1 times the identity matrix. Really, what this ends up amounting to, sorry, 1 second. V2 is going to be V12, V22 is the notation he was using. What this process here really kind of can be shortcut by is just you're subtracting your eigenvalue in the diagonal spots. So I would have skipped this step and done the following. I would have said, okay, my matrix A is this, my eigenvalue is 1. So in the first entry here, I'm going to have -1, -1. In the second entry here, I get 2 minus 0. Basically, you're not changing the off-diagonal entries. So the 2 here and the -3 there stay the same. And then over here, I'm going to get 4 minus my eigenvalue. 4 minus 1 is 3. Times the vector we're trying to find equal to the 0 vector. And now it might even be easier to see how much the same these equations are. If I actually do the multiplication out, the first equation is -2 v12 plus 2 v22 equal to 0. Or in other words, v22 equals v12. And the second equation, I think you all can probably see with your eyes, is going to give you the same thing. -3 times v12 plus 3 times v22 equal to 0 ends up just being 3 times this equal to 3 times this, which means they have to equal each other, just like we found over here. So again, can't emphasize enough, you only really ever need one of these equations to figure out what your values are going to be. What v22 and v12 are going to be. So here, what would I pick for v12 or v1 or v22? What do you want? Pick something. Pick any number but 0. Sure. So my vector would be 3, 3. What else could we pick? 1000. My vector could be 1000, 1000. But the typical choice is going to be what? 1, 1 is going to be the vector we're typically going to write. Anything is fine, but your teacher is going to make the normal default choice of picking the smallest possible integer values. So our eigenvector here is going to be v2 equal to the vector 1, 1. We want to avoid fractions if possible. We don't want to pick giant numbers if avoidable. All right, so now we're going to save this for a moment. We'll come back to it in a little bit here. Let's look at some examples about what we're trying to do with these systems of differential equations. which I'm going to try to write in the way that he has been writing it somewhat. Okay, so let's say that we're going to let x1 of t equal the population of wolves. Typical predator-prey kind of situation. And x2 of t is going to be the population of deer at time t, right? The at time t is implied there because they're functions of time. And then we're going to say that I would probably generally write dx1 dt for the derivative of x1, but I think your teacher really likes to write x1 dot. Right? That means the same thing. Derivative of your thing with respect to what? Always time. If you're writing that dot notation, it always means the derivative with respect to time. And then we're going to say that's equal to, so it's going to be the growth rate of the predator. Right? The rate of change of something is how fast it's growing or how fast it's declining if it's a negative growth rate. Similarly, dx2 dt or x2 dot is the growth rate of deer. Again, growth can be positive or negative. And then there's some expectation that these populations' growth rates depend upon each other, right? If there's more deer, well, the deer can make more deer, but then there's also more deer for the wolves to eat. So the wolves can probably grow as well. So let's say that we have this system of linear differential equations. x1 dot equal to negative x1 plus 2x2 and x2 dot equal to negative 3x1 plus 4x2. So what this is saying is the rate of growth, the rate of growth of the population of wolves is going to be negative the number of wolves, because if there's too many wolves, then there's too many wolves to feed. Like, right, they're trying, like, there's not enough food for all of them. But the more deer there are, the faster they're going to grow. So more deer means faster growth. More wolves means there might not be enough prey for them to all eat. So less wolves is better. We're not concerned that much about the biology. I'm just trying to make it make a little bit of sense. But don't, if you're like, that doesn't sound exactly right, we'll just ignore it. Similarly, the deer over here are happy that there's less wolves, right? If there's less wolves, they're not going to get eaten as fast. And if there's more of them, we can say they can make more of them. Even though, yes, there might be less food than whatever. Okay. So also, we're going to say that our initial conditions are that x1 of 0 is equal to 2. And that can be 2 wolves or 2,000 wolves, whatever we want to pretend like that is. And x2 of 0 is equal to 4. I'm making these up. But often you are given all this information. So you're certainly going to be given a system of 2 linear differential equations and 2 unknowns. And not always, but often you're also given initial conditions. So, yeah. Let's rewrite this linear system of differential equations. So this linear system of differential equations can be written via a matrix. So the A matrix is just your coefficient matrix. It's all the coefficients of these things in order. So it's going to be, I should start, sorry, let me say this first. So it's going to be x dot, which is just the vector of derivatives of x1 and x2. And those are equal to the matrix A, which is the coefficient matrix, -1, 2, -3, 4. Oh, that matrix looks familiar. Times the variable matrix x1, x2. Or if you prefer, x dot equals A times x. And again, I prefer little arrows above my vectors, but you don't have to write the little arrows there. He prefers more of like a boldface notation, which is pretty typical. I can't really write in boldface, but like if you ever look at the textbook, you might notice that vectors are written like in a very darkened boldface, and non-vectors are not, or they might write them with an arrow, but it really depends on the types of them. Okay. He actually did a really good, well, a pretty good, a very detailed explanation of why this equation has the solutions that it has. He did this whole thing where we're saying like y equal to this other thing, and like I really enjoyed it. I was like, oh, this is great. I've never actually had anyone really explain why this equation has the solution it has. We're not going to do all that because we don't need to do all that. It's nice to see, and I encourage you, if you want to see it again, go back and watch his video. I think he did a good job of showing the steps of how we get there. But really what you need to know is that, hey, look, this equation, the derivative of x equal to a times x, looks a lot like this equation. The derivative of x equals alpha times x. With good reason. They are very similar. And if the equations are very similar, the solutions are also going to be very similar. So here, the solution to the derivative of x equal to a constant times x was x equal to some constant times e to the constant times t. We're going to have a very similar answer here. But he did a good job of explaining, like, because he said first, like, y prime is equal to y naught e to the alpha t, and then he multiplied it by the matrix to get the x was this whole matrix thing, which I thought was, again, I was like, oh, that's great. I've never seen that. It's kind of cool. But we're just going to jump to the end and say that the solution, I really should pop in a word there, the general solution to that equation, which I'm going to write down again, to the derivative of x equal to the matrix A times the vector x is given by not just x naught e to the alpha t, but it's going to be given by x of t. Wow, that's a given by x of t equal to, you are going to want to memorize this because you're not going to be able to help yourself but memorize this because it comes up just every time. It's going to be c1 e to the lambda 1t times v1 plus the same thing with twos. c2 e to the lambda 2t times v2. Very, very similar to, sorry, to, you can't really, to x equal to x naught e to the alpha t. We're just taking that and essentially multiplying it by the eigenvectors. This is the general solution to the system of differential equations, of linear differential equations. So let's actually fill in the values here. What we're really saying here is that in this situation where x dot is equal to the matrix A, which is -1, 2, -3, 4 times x, our solution is, all right, well, x of t is equal to, we don't know what c1 and c2 are. We're going to hold off on that. Those are the constants that are kind of just there. But our lambda 1, I said, was 2. So we're going to have e to the 2t times the associated eigenvector, which I forgot what it was. I think it was 2, 3 or 3, 2. I don't actually remember. It's all my notes right here. Why can't I just look at my notes? Because times 2, 3 plus c2 e to the lambda 1, the lambda 2, which was 1. I'm regretting my choices now, times t times the vector, which was 1, 1. And this is the general solution to x1 dot, x2 dot equal to the matrix -1, 2, -3, 4 times x1, x2. Or if you prefer, you could even write it out, right? We had x1 dot equal to -x1 plus 2x2. And x2 dot equal to -3x1 plus 4x2. Right, that was our original system of equations. All these things are kind of meaning the same thing. It's just we have different ways of imagining or writing them. Okay. Cool, I guess. A lot of the time, we're also going to be asked to find the values of C1 and C2 based on our initial conditions. He did it in kind of a neat way where you like take something and multiply by an inverse matrix. Usually that's more work than you really have. So here's the easy way to find C1 and C2. Easy-ish. Easy way to find your constants. So take your initial conditions, which I've forgotten what they were. I think it was x1 of 0 equals 2 and x2 of 0 equals 4. Does that sound right? Yes. X1 of 0 equals 2, x2 of 0 equals 4. And literally, we're going to plug that in. So I want to point out this equation here, this equation here, on the left-hand side, I didn't really write it, but that left-hand side is the vector x1 of t, x2 of t. Right, that's what the big X means. It's just the vector of both components. Just like the x dot as a vector just means x1 dot and x2 dot. It's just the vector of components that have each of those things. So then we're going to plug in t equals 0. So let's look what we get. If I plug in t equals 0, here I'm going to get x1 of 0, which is 2. Yeah, I'm going to write it out. x1 of 0, x2 of 0, which is 2 comma 4. But it's equal to, okay, watch this for a second, C1e to the 2 times 0. Oh, plugging in 0 is great because e to the 0 is just 1. So I don't really even want to write the e to the 0. I'm going to write C1 times 2, 3 plus C2 times also e to the 0 times 1, 1. Yes. Oh, yeah, you could totally make the matrix V, which is the matrix of eigenvectors, and then find V inverse and multiply both sides by V inverse. I guess we'll do it both ways. Do it both ways. Here's how I would solve this. I would say, okay, great. First line of this equation is 2 equals 2 times C1 plus 1 times C2. The second line of this equation is 4 equal to fill in the rest. You have 20 seconds. That's way too much time. Okay, that's enough time. Let's see, 4 equals 3 times C1 plus 1 times C2. And then as long as the numbers aren't terrible, you can solve this in kind of a typical way. I would take that first equation and subtract the second equation to eliminate the C2s and say, okay, great, 2 minus 4, 2C1 minus 3C1 plus 0. So C1 equals 2, great. And then plug that back into either equation. And then 2 equals 2 times 2 plus C2. So 2 minus 4 equals C2. Awesome. Or you could do the thing where you say, I really don't want to do it though, but I will do it for you. That the matrix V, which is just the matrix of eigenvectors, times the coefficient matrix C1, C2 is equal to 2, 4. That's your V there. And this is why I mentioned that you might want to get good at finding the inverse of a 2 by 2 matrix, because then what we're going to say is that C1, C2 is equal to V inverse times the vector 2, 4. Okay, I can find the inverse of this matrix. So I'll remind you all, gosh, with a lot of burping apparently, sorry, that the inverse of a matrix V is first 1 divided by the determinant. So it's 1 divided by 2 times 1 minus 1 times 3. That's the determinant of V. Times, okay, you take your matrix, you interchange the diagonals. So instead of 2 here and a 1 there, it's going to be a 1 there and a 2 there. And the off diagonals stay in the same spot, but you change their signs. So instead of a 1 here and a 3 there, you're going to have a negative 1 there and a negative 3 there. Times C1, C2. Sorry, times, oh my gosh, times 2, 4. Sorry. That's terrible. And so then if we look at this, 2 minus 3 is -1. 1 over -1 is -1. So I have -1 times 1, -1, -3, 2 times 2, 4. I would probably distribute the -1 into the matrix first and say I have -1, +1, +3, -2 multiplied by 2, 4. And then actually doing it, -1 times 2 plus 1 times 4 is -2 plus 4. 3 times 2 minus 2 times 4 is 6 minus 8. And I end up getting 2, -2. 2, -2. Same numbers. Which way do you want to do it? I don't know. This felt like a lot more work to me. And it does feel like a lot more work when the numbers are easy. But when the numbers are trash, usually doing it this way is probably easier. So either way is fine. He might kind of expect you to do it more like this. So you might want to get used to doing it more like that. I'll try to model both ways consistently. So going back to our general solution. The general solution, again, I'll remind you, to this particular system was x of t equal to x1 of t, x2 of t, which was c1 e to the lambda 1 times t times v1, which was, why can't I remember what it was? 2, 3, plus c2 e to the lambda 2, which was 1 times t. By the way, that was probably a bad choice. I should have just said lambda 1 was 1 and lambda 2 was 2. It would have been more sensible in my brain, but sometimes we make bad choices. So that's the general solution. And then the particular solution, we just found C1 and C2. The particular solution for x1 of 0 equal to 2 and x2 of 0 equal to 4 is x of t equal to C1, which was positive 2, e to the 2t times 2, 3, plus C2, which was negative, so it's like minus 2, e to the t times 1, 1. Cool. It's kind of nice to think about what's happening to the wolves, and I know, right? These are still wolves and sheep, not sheep, deer. What happens to the wolves and sheep as time goes on and on and on and on and on? I will point out, I know what's going to happen based not on what I'm about to do, but based wholly on the fact that I know that my eigenvalues were both positive. So because both eigenvalues were positive, I know that I have an unstable node as my equilibrium. And we'll talk more about this later. I'm just trying to give you kind of like the look ahead. Based on the eigenvalues, I can say that my equilibrium, which is the origin, right, 0, 0 is almost always the equilibrium. Also, I'll point out, right, if going back to my original equation for just a second here. Let me point out, if x1 and x2 are both 0, then the derivative would be equal to 0, so you wouldn't get any more, right? If the derivative of x1 is 0, that means it's not changing. Similarly, if x1 and x2 are 0, this would also be 0. So 0, 0 is almost always, at least in these situations, the equilibrium, because if you have 0 of everything, then the rate of change is still going to be 0. If the rate of change is 0, what you've got is what you've got. You're not changing. So if I start with 0 and my rate of change is 0, then I'm never going to change from 0. But if I have a little bit more or less, like if these are both not 0, then my rate of change is going to be positive. And here, since my eigenvalues are positive, once I have a little bit of stuff, I start moving further and further away from the origin. That's not always true. If my eigenvalues have been negative, I actually get pushed back towards the origin. Here's why. If you look at this here, again, remembering that this is x1 of t, x2 of t. Well, let's just write what x1 and x2 are separately. So this is something I want you to get good at. X1 is just the top row of entries. So here, x1 of t is just the top row. So it's 2e to the 2t times 2 minus 2e to the t times 1. Or I might rewrite this as 4e to the 2t minus 2e to the t. And to make it easier to see what's going to happen, like, because here, if t goes to infinity, this is infinitely large, and so is this, and infinity minus infinity is kind of weird. But if you factor out a 2e to the t, you're left with a 2e to the t minus 1. And now you can kind of better see that if t gets infinitely large, then that's going to be infinity, and that's going to be infinity as well. Infinity times infinity is infinitely large. Similarly, x2 of t is 2e to the 2t times 3 minus 2e to the t, which is going to end up being, let's see here, I'm going to factor out the 2e to the t again, just for fun. I'm left with 3e to the t minus 1. So again, both we can see that the limit as t goes to infinity of x1 of t is infinity, and the limit as t goes to infinity of x2 of t is infinity. So what we're saying is based on this very, very simple model, it doesn't account for a lot of other factors with predator and prey populations. If we just let time go on and on and on forever and ever and ever, both populations would grow without bound. They both get larger and larger and larger. Kind of neat. A useful tool that I just actually found. And I posted this on Canvas just this afternoon. He was doing some stuff like this in class as well. There's a graphing tool, not this one. This one's fine, but the other one I've got is actually better. It's over here. It's the bottom link in the modules in Canvas. You can set up, so here, and they do use x and y instead of x1, x2. So pretend like x is your x1, y is your x2. So my dx dt is negative x plus 2y, just like my equations, right? That's my first equation. dx1 dt is negative x1 plus 2x2. And dx2 dt or dy dt is negative 3x1 or negative 3x plus 4y or 4x2. And if you do that, and you do want to choose system here, you don't want to choose one of these other ones here because they're different things. It'll give you the direction field. And then you can click on any point, and it'll show you, like, if you start, for example, if you start at the point 2, 4, which is actually, you know what? You can try and click on it, but there's a better way. You can actually click on this and then plug in the point you want, which I learned when I was, so it's kind of cool. It's much better. It's much easier than trying to click on the perfect point. But if you do that, then it shows you, it shows you, look, if you start right there, then you're just going to go off, bigger and bigger and bigger. And you can definitely make your table, nope, not your table. Sorry. You can make your something. Oh, if you click on the gear thing here, you can make this much larger. So you can go like way super big if you want. It's kind of silly to go this big, but it doesn't really show you a whole lot more. All right, that's a little bit more like, oh yeah. It shows you that if you start here, you're going to just go that way, both the population of wolves, X, and the population of deer, Y, are getting larger and larger and larger as time goes on. Also, this thing over here, which is the time plot, shows you what's happening to each population as a function of time, right? So time is the x-axis, and X and Y, or the outputs, are your different graphs here. And we can see, oh yeah, as time goes on and on and on and on, it also traces the point out over there, which is kind of cool. You just get bigger and bigger and bigger. This doesn't always happen, but it definitely does always happen if both eigenvalues are positive. Because if you look back to the work we were doing, you can kind of see that both eigenvalues being positive here means you get e to something really, really big and e to something really, really big. And that gets really, really big. On the other hand, we don't have enough time for this today, but definitely on Monday, if these eigenvalues have both been negative, then a negative number times infinity goes to negative infinity, and e to the negative infinity is the other side of the e to the x graph, which gets closer and closer and closer to 0. So if both eigenvalues are negative, we actually do the opposite thing and we get pushed back towards the origin. The bigger picture here is that you can fully classify what kind of equilibrium you have: a saddle, a node that's stable or unstable, a spiral that's stable or unstable, or a center. I know these words might not all seem super clear, but we're going to talk about it next week. You can fully classify all of that based solely on what your eigenvalues are doing. So the eigenvalues are really kind of, now you still can't find the solution to the system without finding the eigenvectors and all the other stuff, But if you're just asked to classify a system, tell me if it's a saddle, tell me if it's a node or whatever, that is purely based on what are the eigenvalues. So that's why you want to get really good at finding the eigenvalues without too much effort. All right, I think that's enough for today. Also, it's 2 o'clock. I will see you all next week. I have office hours over in Dutton if you want to come